first lecture in the annual series in honor of the great mathematician Andrei Nikolaevich Kolmogorov. First of all, I must apologize that the principal is unable to be here this evening. He's at the annual residential conference of Universities UK. God bless him. My name, for those visitors to the college who don't know me, my name is Norman Gower, and I'm standing in for the principal this evening by virtue of the fact that I'm the chairman of the organising committee for this series of lectures. It so happens that I'm also a past principal at Royal Holloway, so it's great fun to be back on old haunts, and it's a great pleasure to be here this evening. I'd like to thank the Royal Statistical Society and the British Computer Society for their support for this event, and the Department of Computer Science here at Royal Holloway for doing all the work. It's particularly appropriate that the department should be hosting this series of lectures because it itself is doing such outstanding work in the development and the application of ideas that were of particular interest to Kolmogorov. It's hard to imagine a more appropriate person to inaugurate this series than Professor Solomonoff. He is without doubt a world leader in his field, and it's a true honor to have him with us this evening. He not only fits the criteria for these lectures by virtue of his outstanding work in areas connected to the work of Kolmogorov, but he was, of course, there at the start of complexity theory, developing the ideas of complexity independently of Kolmogorov and from a different starting point. It's probably true to say, may not be true to say, but it's probably true to say that Kolmogorov's primary interest in complexity was to find a way of connecting his theoretical basis for probability with more intuitive and familiar ideas of probability. Professor Solomonoff has always had a particular interest in the practical applications of algebraic complexity, and it is this that we are to hear about this evening. And so, without further ado, may I invite you to give this evening's inaugural lecture in the annual Kolmogorov series.
Second topic is how to use this distribution to get very intelligent machines. Many years ago, in 1960, I discovered what we now call the universal probability distribution. It's the probability distribution on all possible input strings of the universal computer with random input. It seemed to solve all kinds of prediction problems, and it seemed to resolve serious difficulties in the foundation of Bayesian statistics. Here's how it works. Supposing we have a string X, and we want to know its universal probability with respect to machine M. There'll be many inputs to machine M that could give X as output. Now, supposing S sub I is the ith input to that machine that will give X as output. That means you consider S to be a string, S sub I to be a string, and it's going to be a program for machine M, and it's going to have the machine M will probability, when we feed random bits into this machine, the probability of getting that particular string is just 2 to the minus length of the string. Because if it had 10 bits in it, if L was 10, the chances of getting any particular 10-bit string would be 2 to the minus 10. So this expression gives the probability of that particular program. And if we consider all possible ways of getting, of achieving X as output, we just sum over all of these programs, and we get this universal probability of X, which is what we have here. We just sum over all of these probabilities to get the total probability of all programs. Now, it's easy to use this distribution for prediction. All you do is this. Supposing you have a string X, and we want to know the probability that 1 is going to be the next symbol. Okay, that's a model for extremely general kind of sequential prediction. So all you do is you take the universal probability associated with this, with X followed by a 1, and you divide it by the universal probabilities set associated with the thing, next bit being 0 and the next bit being 1. So similarly, we get the probability of 0 being the next one. Now, 5 years later, in 1965, Kolmogorov had not yet read my paper, and he independently discovered Kolmogorov Complexity. The Kolmogorov Complexity of the string symbols X is the length of the shortest program for a reference computer that produces X as output. It's closely related to the universal distribution, and you see why this is true. If K is the Kolmogorov complexity of X, that is the shortest program for it, then 2 to the minus K is the largest term in this sum. And the sum, it's a sort of approximation of the sum. It's not a particularly good approximation, but it is an approximation, and it's good enough for some applications. Initially, Kolmogorov was interested in this complexity as a way to define randomness, and he was interested in the mathematical properties of this concept of complexity itself. He was surprised to learn of my earlier work on inductive inference, and he publicized my discoveries in the Soviet Union, and for many years it was much better known there than in the United States. I was puzzled that Kolmogorov hadn't thought of using these concepts for inductive inference. He certainly done a lot of important work in probability. One of his first great works was the axiomization of probability, and he had done an enormous amount of important work on practical applications of probability. I asked Leonid Levin, who was one of the students at that time, how it was that Kolmogorov had missed this important discovery. Leonid suggested that inductive inference was at that time not really a mathematical problem. I wasn't much satisfied with that idea at first, but thinking about it later, it might have been that at that time, 1965, there was no good general definition of induction, no general criterion for how good an inductive system was. After my initial discovery, I tried to find a good criterion for the accuracy of this prediction method. I finally thought of a good criterion. This is what it is. Supposing we had some unknown probabilistic algorithm, and it could be described in a finite number of bits. And this algorithm produces a long sequence of symbols according to its probabilistic rules. Okay. Then we have this universal induction system, and it's supposed to give probabilities to each symbol in terms of the previous symbols. It does its own induction, it has its own way, own rules of very good induction system and a long enough sequence, the probabilities given by the true generator of the sequence and the one that is trying to approximate it should converge so they're all, eventually they're about the same. So that's the criterion of a good induction system. While the criterion would seem very reasonable, I was at first unable to prove it. Well, in 1968, I was asked to review a paper on inductive inference by David Willis. Though I was familiar with the ideas in his paper, it took me about 6 months to really understand the paper. Willis had taken my system for induction and made it into an exact, rigorously defined system. He had an error criteria satisfied, but certainly not good enough to convince a person that the system was all much good for a prediction. He showed that the average ratio of the correct probability to the estimated probability approached 1 as the length of the data sequence increased. But the individual probability ratios could be quite large or quite small. And the true and the estimated individual probabilities could be actually quite different. So the fact that the average value of the ratio converged really wasn't a very strong argument. However, I was able to improve this result and show that the expected value of the square and the difference in the probabilities between the correct and the estimated values approached 0 faster than 1 over n.
What this means is this. Supposing P sub m is the probability. We have a sequence of bits. A sub 1, A sub 2, A sub 3. A is a string. And we want to predict the next one. So this is the probability that the next bit will be 1 as given by P sub m, the universal distribution. And this is the probability that the next bit will be 1 as given by the algorithm that actually generated the sequence. And this is the difference between the two, and we square this. And we take the sum of those for all of the bits in the sequence. Now the idea here is that I've shown that this summation, the expected value with respect to the device that generated the sequence is going to be less than this expression here. So that, and this is a constant that is independent of how long the sequence is. So the result is that the total amount of error is going to be bounded by a certain amount, no matter how long the sequence is. The total amount of error is going to be bounded. So this means that the errors have to get small very, very rapidly, actually smaller than 1 over n, where n is the length of the sequence. This constant here is natural log of P sub 0. P sub 0 is the probability assigned by the reference machine to the device that really generated the sequence. So in some sense, the generator of the sequence is something that's easily programmed, sort of easily understood by the machine. Then this expression will be, then the thing will converge very rapidly. On the other hand, if the expression, if the algorithm that generated this sequence is in some sense very, very distant, and the machine thinks it's very, very unlikely, then this will converge very, very slowly. But it will converge, and it will converge as 1 over n. So this was an extremely long result. showed it was also true in a slightly different way for algorithms that had significantly long descriptions. I call this result the convergence theorem because of the convergence of the error to zero. It really seemed to make it clear that the universal distribution gave very good probability estimates. I sent in a strong recommendation that Willis's paper be published with no revisions, but the other reviewers had already rejected it. They felt that it had little to add to my original paper. As an aside, I later found out who the other two reviewers were, and they were both real experts in the field of the paper. They were really smart guys, but they didn't get, well, anyway, I wrote Willis telling him what a great paper it was and suggested that he send it to another journal, and he did this and was published in 4 years. Now, this first convergence theorem was for a normalized universal distribution on potentially infinite sequences of symbols. Peter Gotch showed that it was also true for an unnormalized distribution. An unnormalized distribution seemed to me to be not nearly as good an approximation to the original sequence. And it turns out that there is an appreciable difference between using the normal unnormalized and the normalized distribution as an approximation to the true probability. The normalized one gives much better results normally. I didn't realize it until recently. The convergence theorem has been extended even further, though, and Marcus Cutter showed that first it worked for arbitrary non-binary alphabet, which was no surprise, but he also showed that it was true for a variety of loss functions, and one of them extremely general. And this is rather important because there's been a lot of recent work on problems of prediction with unusual or different loss functions from the mean square loss function that we used in this particular paper. Recently, though, I showed that this convergence theorem is also true for grammatical induction. In this case, the data is just a set of strings, finite strings. They could be the accepted sentences, say, acceptable sentences in some formal language or in some real language, actually. I also showed that it worked for operator induction, in which the finite strings are the probabilistic answers to questions that have been generated by an unknown stochastic question answering algorithm. I'll tell more about this later. While the accuracy of the universal distribution as a predictor is certainly important, there are other important features. One of the things that's nice about it is that we could use it to predict on non-stationary time series. This is pretty important. Another thing is we obtain an optimum solution to the problem of overfitting or underfitting data. And because of this optimum fitting, there's no need to divide the data into a training set and a test set. And this is quite revolutionary. It's possible to use another possibility is possible to use partial recursive functions to model our data. To my knowledge, no one has actually tried this, but the system I will describe later will try it. Whether it gets better results than using only recursive models remains to be seen. Now, while all these features are very beautiful, there seemed to be at first a very serious problem, that the universal probability was incomputable. Surprisingly enough, this turned out to be not a bug, but a feature. Before I explain, a brief discussion of uncertainty in prediction. There are two kinds of uncertainty in statistical results, at least
The best known is uncertainty in probability values due to finite sample size. If you have a binary string with n bits and half of them are 0 and half of them are 1, then the probability of 1 being the next bit is about 1/2 plus or minus 1/2 divided by the square root of n. So the longer n is, the less error you have in your prediction. Now, all prediction with finite samples have this problem of sample size, error in prediction due to sample size. The kind of uncertainty I'm going to talk about, however, is not due to sample size. It's all due to model uncertainty. When analyzing empirical data, there are normally an infinite number of models that could be used to analyze the data. Some of them will give good predictions, others will give poor predictions. In any finite amount of time, you can only evaluate a finite number of them. So the universal distribution tells us that whenever we find a model that seems to fit the data well, we can't be sure that there isn't another model that will give much, much better predictions. There's no way to avoid this. In finite time, you can only consider a finite number of models. The incomputability of the universal distribution is related to the fact that it evaluates all possible models, and it takes an infinite amount of time to do it. Let's look at it another way. The exact value of pi, or the square root of 2, is in a certain sense incomputable. But we know how to make approximations, and we know that the approximations will eventually converge to correct values. For the universal distribution, we can also make approximations, and we know that they will eventually converge to correct values. However, the difference is this. In the case of the approximation for pi, we know at each point, or have a good upper bound on the limits of error. In the case of approximations to the universal distribution, at no point in our approximation can we know how much error there is. Or we have an upper bound, but it's so large that it's not of any use at all. Furthermore, it's not a small effect. No matter how many models we've tried and how long we've tried, there's always a very real possibility that we have not yet considered a particularly good model, and that we could find it if we just spent a few more minutes to search. Now, it turns out that any complete predictive system, one satisfying the convergence theorem, must be incomputable. And this is not difficult to show. For any computable prediction system, there must be regularities that are invisible to it. And if the data has those regularities, we have errors of unknown size. And they can be arbitrarily large. So, all computable prediction methods, not just approximations to the universal distribution, have errors of unknown size. There's no way to avoid this. It's a property of probability itself. Now, certain scientists have expressed much confidence in their estimates of probability of catastrophic failure in nuclear reactors, national defense systems, and in public safety regulations for genetic engineering. The considerations I've mentioned lead one to question this confidence. There's a tendency to try to deal with this issue by avoiding the use of the incomputable universal distribution. But this doesn't face the problem. The problem is that empirical probability itself is incomputable, and approximations to it always have errors of unknown size. The study of the universal distributions has made this uncertainty uncertainty clear, and we shouldn't punish the reporter for bringing the bad news. Another apparent difficulty with the universal distribution is its subjectivity. When the universal distribution is mentioned, there are two possible meanings of universal. First, that the error will converge to zero rapidly if the algorithm generating the data has a small finite description. This is true for all such generating algorithms. This is what I mean by universal distribution. Now, another interpretation of universality is that we can usefully employ the same universal distribution for all problems. This is what I call a half-truth. The same universal distribution will indeed work for all problems, but for most it'll work very poorly. The errors will converge very slowly. To get good predictions, we usually have to use a different universal distribution for each problem domain. And the system that I'm going to describe is built around that idea. When I speak of a priori distribution or a prior information, what I mean is information available before the data in the problem is known, and so on, that I mean. As soon as some data is used to solve a problem, the statistician's a priori is updated to reflect that new information. So we have a continually changing a priori distribution throughout the life of the statistician that reflects the problem solved during his or her life. A philosopher may ask, in fact they do ask, is there not a universal a priori probability distribution in which you have no prior information? Well, let me give you an analogy. If I had no food, water, or air to breathe, what would I do? Well, I wouldn't do very much. I'd probably die quickly. If I had no a priori information, there would be very little that I could do to solve a statistical problem. And that's it. A priori information, if you have no a priori information, and you want to have a sort of a priori distribution or anything like that, I think the distribution would be of approximately zero value. You have to have real information before you can do any kind of prediction at all. The nature of the a priori information that a person has is difficult to characterize. However, we normally have to use only part of our a priori information. For a specific, well, let me talk a minute. I said that fortunately we don't get into this position where we have no a priori information. Normally we're born with a fairly good a priori knowledge of the world we live in. This a priori information enables us to learn to walk, to talk, and communicate. And it's very unlikely that we ever learn these things if we didn't have this a priori information. The nature of the a priori information that a person has after he's been living a long time is extremely difficult to characterize. However, we normally have to use only part of this information. For a specific problem, we often have very strong ideas as to what functions would be useful to solve this problem. In this case, we would augment the instruction set of our universal computer with those particular functions. If we're less certain of what functions are needed, we might use a set of instructions that has been designed for a more general prediction method. Such sets of instructions are C++ libraries or parts of Mathematica or Maple or MATLAB. If the instructions we inserted are not relevant to the correct probability function, the convergence rates will be very slow, but it will eventually converge to the correct values. So, the subjectivity, the fact that it is based on our choice of which universal machine to use, is characteristic of of all prediction systems based on a priori probability distributions. The choice of a universal machine and its instruction set is a necessary parameter of the system that enables us to insert a priori information into it. The dependence of the universal distribution on choice of machine is not a bug in the system. It's a necessary feature. Now, my main goal in studying universal distributions wasn't especially prediction, but strong AI. For me, this means writing a program that could work most scientific problems much better than a human can. Many years ago, about the time of the discovery of universal distribution, Newell and Simon programmed GPS, the general problem solver, a program that was meant to solve a great variety of problems. In fact, it only solved a small subset of what we call inversion problems, and in a very deterministic way. But perhaps its most important defects were that it had no concept of probability, and it was absolutely unable to learn anything. If you gave it a problem, and after a long time it finally solved it with great difficulty, then you gave it the same problem the next day, it would solve the problem in the same difficult way, taking the same long time. Nevertheless, the AI community was pretty much taking the Newell and Simon approach, and for many years there was relatively little work in AI involving learning or probability. I say relatively little, but there was, and it kept growing. Anyway, in about 1985, about 25 years later, at an annual meeting of the American Association for Artificial Intelligence, a vote was taken and it was decided that probability was in no way relevant to artificial intelligence. A protest group quickly formed, and the next year there was a symposium at the AAAI meeting devoted to uncertainty in AI, most of which involved probability and learning. The symposium has continued to be a yearly event to the present day. As part of the protest at the first symposium, I gave a paper on applying universal distribution to problems in AI. This was an early version of the system that I've been developing since that time. My interest has always been in a much more general class of problem solver than that envisioned by Newell and Simon. The system I've been working on solved problems with both probabilistic and deterministic answers, and learning is an integral part of the system. It's designed to learn to solve two kinds of problems. Almost all problems in science and engineering are of these two kinds. The first kind is function inversion. These are the P and NP problems of computational complexity theory. They include theorem proving, solutions of equations, involved integration, and a lot of other things. The second kind of problem is time-limited optimization. Inductive inference, surface reconstruction, image restoration are a few examples. Designing an automobile in 6 months, satisfying certain specifications, and having a minimum cost is another example. The general understanding of probability that we've obtained through the universal distribution enabled us to make programs that can learn to solve both of these kinds of problems in a manner that seems to follow the acquisition of new skills by humans. In the infant machine, we have a bunch of problem-solving techniques, and these are put into the machine by the trainer or the designer. We have a conditional probability distribution based on the previous experience of the trainer and the machine that suggests which problem-solving techniques should be used with which problems. Now, the experience system has many more problem-solving techniques. When the system is given a new problem, when the experience system is given a new problem, It uses its previous experience with similar problems to decide which problem-solving techniques to try and how much time to spend on them, which is the important part. This experience is embodied in a general conditional probability distribution. This distribution gives the probability that each problem-solving technique will be the best technique for solving any particular problem. The condition on the conditional probability distribution is the problem to be solved or descriptive problem to be solved. And the distribution itself is going to be on the probability that each problem-solving technique will be the very best way to solve that particular problem. Now, the system uses this probability distribution to decide how much time to spend on each problem-solving technique. After the problem is solved, the general condition of probability distribution is modified. The problem-solving technique may be modified, augmented, or completed in view of recent experience. The last talk I gave at Royal Holloway, I guess, maybe 5 years ago, was at a symposium on the importance of being learnable. It was a description of some ideas I had on transfer learning, how learning in one domain could utilize information in other apparently completely different domains. Now, much of my recent work has been in developing and understanding the updating system that enables the general conditional probability distribution to implement direct and transfer learning from both successful and unsuccessful problem-solving event trials. And that's it. So are there any questions that you have, or suggestions or comments? Oh, good. Yes.
Mind this point about a priori knowledge.
Yes.
As you spoke, it connected in my mind with a debate among psychologists about how children learn language.
Yes.
And as you probably know, Chomsky and Steven Pinker and people argue that language is such a complicated thing that children must have a lot of inborn knowledge. And other psychologists have taken a contrasted view. From what you're saying, it sounds as if you would support the Chomsky-Pinker position.
Yeah, very definitely. I had this idea long before I was reading Chomsky. Interestingly enough, the basis of this was what happened was, the way I discovered this almost was this. There was a conference, the first sort of workshop on AI in 1956, and everyone working on AI over the world, well, not everyone, but a lot of people came there. There weren't a whole lot of them. And as a result of that sort of workshop, I wrote a paper called Dr. Bitford's Machine, which is sort of the beginning of the work I'm doing now. At the same conference that I was giving this talk, Chomsky gave a talk on 3 models for the description of language. And I had gotten into a lot of trouble with the system I had. I thought when I started the system that I knew enough about probability that I should be able to deal with any problems in learning or anything like that. I was wrong. However, I worked on this a long time, and then I thought that some of Chomsky's ideas were very close to some ideas that I had about generating complex objects for induction, and I was interested in using form languages for induction. So I devised a probabilistic version of Chomsky's languages, and I tried to find the most general probabilistic language, which turned out to be the universal distribution, and that's how it all started. I'm sure that Chomsky is sort of right about this stuff, that it would be absolutely impossible to learn languages as rapidly as children do without a lot of a priori knowledge. And what they're doing now is trying to find out the nature of the general grammar that is sort of built into children at birth. One of the really difficult things about language, though, is this, that we have grammar rules, and every language, or most languages, have grammar rules and things like that. But the fact of the matter is that while people use grammar rules to some extent to generate sentences, one of the things that happens to languages, people make up their own little grammar rules that are easily figured out by other people. That is, they make inductive generalizations of any kind at all, and these are picked up by other people. And the language is constantly growing and constantly changing. And it usually has in the background some basic grammar rules, but deviating from them is always happening. And if you listen to people talk, most of the things they say are completely radical. However, still, to even begin to understanding any of this stuff, before you get to the point where you start changing the language around, I think you really do have to have some basic a priori knowledge, and this is probably built into us, or certainly built into us. There was another problem about this, though, and that in physics there's a thing called the anthropic principle. The idea is this, that if the laws of the universe seem to be designed for man alone, that if the constants in our universe were just slightly different from what they are now, the universe would be so different that stars would not arise as a whole. We'd never have a place to live at all. So the question was, how does this thing arise? We don't know, really. So one of the postulates is that there are many different universes being generated at random, and one of them happens to be us, and we happen to be the one in which the constants are right for our coming into existence. Well, there's a similar problem in epistemology, really, about where we get this a priori information. I'm certain that the way we get it is by evolution, that very simple creatures have very simple a priori ideas about the universe around them, and they're able to learn a little bit, but not very much. And creatures evolve, and as they evolve, they become better and better at taking advantage of regularities in their environment to keep them alive and to reproduce. Life in general is the ability to reproduce in a very noisy, difficult environment. It's possible to make systems that can reproduce in a very, very restricted environment, like crystals, for instance. They have to have, say, a solution surrounding them with a high concentration of certain salts, and they can't, under those conditions, they could grow no other ones. Certain computer programs could easily reproduce because the CPU has a copy instruction. But the really interesting cases are situations in which we have programs that can reproduce when there's noise, or in general creatures that can reproduce in very adverse conditions that they were not specifically designed for. And that's what's interesting about life. So what happens is we have life evolving to be able to deal, well, to some one direction that life evolves at least, is in a direction of being able to deal with more and more difficult, more and more complex environments where it is difficult to stay alive. And that's how we got here. Now, we wouldn't be here if we did not have a sequence of, a training sequence of challenging environments that made it necessary for us to evolve to get to this state. So in that sense, that's part of the anthropic principle also, that we somehow have to have had that particular sequence of things happening, or else we wouldn't exist. Yes?
One of the problems with artificial intelligence, with the field of artificial intelligence, is that although everyone can identify examples of intelligent behavior, examples of intelligent solutions, I haven't really seen a general definition of what intelligence is. I'm wondering if...
Okay, well, for a long time, there was, I won't say a long time, one criterion that had once been proposed was Turing's test. You're probably familiar with that. And that the idea was if you had a machine answering questions via teletype or some method like that, so you can actually see the machine, could you tell the difference between a machine and a person answering a question? It has become abundantly clear that this doesn't answer the question at all. It becomes a question of how do you go about fooling the person. And you can write programs that will fool people. That's real. As a matter of fact, this test had been passed, as far as I can tell, a long time ago. Douglas Lennon went through a program called AM, and some people were playing with the program, and the answers it gave were so, they thought, intelligent that they felt that there was really, that Lennon was cheating, and that he was really giving, there was a man inside the machine. Now, the kind of intelligence that this machine had was really pretty nominal. As far as speaking English, it did speak English, but it had it had a very limited vocabulary, and it would speak English as well as the machine at the checkout counter of the supermarket does. It just prints out things. It really didn't know what it was doing. But it did, was able to do some fairly interesting things in the sense of finding reasons for certain kinds of reasoning, reasons for making certain kinds of deductions. So the guys looking at the machine really felt that it was pretty intelligent. I myself have never gotten into this problem at all. And I felt one of the reasons they wanted this was that you could use a criterion for intelligence in a kind of hill climbing technique. What you do is you work on this machine a little bit, and if it gets more intelligent, you try and move in that direction more. Or you get to a new position and you try to make changes and so forth. To do that, you need a very good, very sharp definition of intelligence, and I don't think there is anything like that. Any kind of criterion you have a lot of noise in it, in the feedback. So you could do this hill climbing, but it would be very difficult. My own take on this is I'm really not interested in that at all. And I feel that I personally could tell whether a machine was doing something useful or not. That at the high level, it's certainly easy to tell that the machine is being intelligent. It's solving problems that you can't solve and no one else can, or it's doing things much more solving them much more rapidly than you can. So in that sense, you could recognize high-level intelligence. The difficult part is to recognize, one, not so intelligent things, and whether you are on the path to it. And this is what I think I understand enough. My theory is that new good ideas are made by combining old good ideas. And an intelligent system will do this well. And that's about it. And you can watch it doing things, and if it doesn't, and if what it does doesn't seem to extrapolate to doing more complex problems, then as far as you're concerned, as far as I'm concerned, it's not intelligent. I think I know enough about my system anyway to tell whether it's getting anywhere, whether the new problems it solves are indeed more difficult in a useful way than what I had before. In fact, recently, a colleague of mine programmed a machine to do something like something like the system that I've been writing about for all these years, and able to do an interesting thing. What it did was this. He gave it a particular problem. It's a classic problem in AI called the Towers of Hanoi. You have a bunch of piles of disk, and you have to transfer one pile to another pile. And normally, if they're n disk, it takes something like 2 to the n transfers to do this. And most programs find it very difficult to learn how to do it. Anyway, so we gave this problem to the system, and it wasn't able to do it. That is, it wasn't able to get the recursive solution. It did solve it for a few values of n. So then what he did was he gave it another problem that required a recursive solution also. The problem was generating the sequence of n1s followed by n2s. He gives the machine the number n, and it's supposed to give that output. Now, he could easily learn to do this for 1, 2, and 3, and so forth. And eventually, it got a recursive solution. It took a long time to get it. It got a recursive solution to it would do it. So after it solved the recursive problem, its biases on what trials it would make were considerably changed. And when it gave it the problem of the Towers of Hanoi, it was able to solve it. It took a long time, but it did. And to my knowledge, no other AI system has done that particular thing. Now, I looked at this program very carefully, and at the present time, I'm not really sure that it's doing anything useful. It's very difficult to analyze these things, and I really don't know. I'm interested in it, and I would like to modify his methods to use in my own system. And the question is, can it be done? And at the present time, I'm not sure. It's often a very difficult thing to tell. The real test of the system, of the whole thing, though, is can you get it to work progressively more and more difficult problems empirically? So in spite of any analysis I might make, if this guy is able to get it to work more and more difficult problems that are recursive or anything like that, then he's right. Yes?
If you were a young PhD student at the start of your PhD, how do you spend the next 3 years?
What?
If you were a young PhD student at the start of your 3 years, how would you spend your next 3 years?
know what I would say. See, you mean you're interested in AI, say?
I should say I'm at the end of my PhD.
Oh, you're at the end of your PhD?
Yeah.
Oh, so you want to be a postdoc?
Hopefully, yeah.
But you're in this? Are you in this field?
Genetic programming.
Okay. Well, as you probably know, Koza has been doing some interesting work in genetic programming, and he's been getting some interesting results. My own impression is that the system he uses is essentially extremely inefficient, and that usually genetic programming is inefficient. The very nice thing about it, though, it is usually universal, so that any conceivable answer to the problem is in some sense accessible to it. It may be that it takes too much time, though, and as advising you, I don't know what to say, really.
I think we'll draw that to a close. In case somebody else asks what they're going to do. I'd like now to invite Professor Phil Darby from University College to move a vote of thanks.
Well, I'm sure I speak for everybody when I say that we couldn't have had a more appropriate and stimulating inaugural Kolmogorov lecture. I found depths of understanding and breadth of the overall picture in this brief presentation, which have really left me with plenty to think about for months and years ahead. I think it's particularly appropriate for the current occasion. We're here to honor the memory of Kolmogorov, whose 100th birthday it has been. And as the range of activities in the mathematics and outside mathematics that Kolmogorov undertook is phenomenal, but he is particularly well known for his work in probability on the one hand and complexity on the other, and it's not just on the one hand on the other, because they do of course have very strong links, although Kolmogorov himself probably didn't make those links as strongly as Ray Solomonoff has done. It's interesting and appropriate too that as well as the local Computer Learning Research Centre, this meeting is being sponsored by both the British Computer Society and the Royal Statistical Society, and both Kolmogorov and Solomonoff have had one foot firmly in each of those camps and done a lot to bring those two together. I myself have for some years been trying to occupy some of that no man's land, not many man's land anyway, between the two subjects, and finding it utterly fascinating, coming from the statistical end and looking over to what's going on in computer science, and there's so much that needs to be transferred between the two. There are places like Royal Holloway where that is an active thing that's going on, which I'm very impressed by. Ray Solomonoff has, well, he hasn't so much brought together Kolmogorov complexity and probability as started all off in the first place, before Kolmogorov. So we owe to him the genesis of these fascinating ideas. And the whole business process of learning and induction, which has been so important to statistics for so long, is now an enormous research field in computer science. And I know we statisticians have a lot to learn from it. I'd actually like to get just a tiny bit technical. I don't want to bore you in it, because I'm sure I can't talk about these things with the same light touch that Ray has done. But I was very interested in a lot of the specific points made about merging of the specific distributions and the universal distribution, for example. There's one point which I think could be brought into this equation, wasn't specifically mentioned, and that's thinking not so much about whether two different distributions are going to end up saying essentially the same thing, as thinking more about the fit between an attempted explanation of a data sequence and, in some sense, the data themselves. How well does the explanation fit, not the best explanation, but the data? And we need different criteria for thinking about fit between probabilistic explanations and data, but these have been produced and they can be done. And they do actually tie up very closely with many of the ideas on, for example, merging that we've heard about tonight. And you can show that two different systems which, in a certain sense, both are good explanations of data must merge for that particular data sequence. And what can they merge on but the universal probabilities? I'm also interested very much in the latter parts of the talk about the idea of learning from your mistakes and doing better and tuning things, and the idea of self-tuning universal machines, as it were. But of course, even a self-tuning universal machine, which you, as you go on, learn new things and you change and you change your machine a bit, even that can be regarded as issuing a single sequence of probabilistic predictions for the sequence you've got to see. And in that sense is nothing else than another universal machine. So it's just another way. Is there a universal machine, in other words? That would do the self-tuning. And I think the answer is, well, maybe, but but that's not the important question. The important question is, how can we approximate it? And that's what I was particularly fascinated by the specific ideas that Ray Solomonoff was bringing forward in how we can actually approximate these utterly uncomputable things and never know how well we're going to do, but at least do a jolly good job. So I look forward to looking at that more closely. As I'm sure you can tell, I've been enormously stimulated by this lecture. It's also not very often the answers to questions are as stimulating as the lecture itself. I've appreciated it enormously, and I'd ask you to all join with me in a vote of thanks to Ray Solomonoff.
Now, we can't have a drink yet because we're not quite finished. As part of the institution of the Kolmogorov annual lecture, in recognition of the achievements of the lecturer, there will be presented a silver medal. And so this is the first of such occasion. It's a very auspicious occasion, and I'll ask Alex to perform the duties. Ray, come forward. Now, you're all very, very warmly welcome to a drinks reception in the picture gallery. For those of you who don't know where the picture gallery is, just follow somebody who looks as they do. And you will learn quite quickly. Very much.